In this video, we're looking at rules for assigning oxidation numbers. So this video will have a bunch of examples on how to assign oxidation numbers. What you may want to do before continuing this video is to print out the rules for assigning oxidation numbers from either the other video or the PowerPoint presentation, so you can kind of look on with the rules as we go through some of the examples we're going to do in this specific video. So the first rule for assigning oxidation numbers deals with elements in their natural elemental form, not combined with anything else. And the rule said that the oxidation number for those elements in that state would be 0. So if you had a chunk of copper, a piece of copper pipe, well, that's copper by itself. The oxidation number for that would be 0. The graphite you might be using in a pencil, or the diamond jewelry that you might have, is just the element carbon by itself. It's not combined with anything else. Being it's not combined with anything else, that oxidation number will be 0. Nitrogen gas, what's in the air you're breathing right now, even though it's N2, it's still just nitrogen combined with nitrogen. It's all by itself. It's not combined with anything else. That oxidation number would be 0. Same thing for the oxygen that we're breathing right now. The oxygen we're breathing right now is that element all by itself, not combined with anything else. That oxidation number is 0. Remember what our oxidation numbers tell us. They tell us the electron richness or poorness. Well, to be able to do that, we have to have a baseline. And that's what this first rule says, is it sets the baseline for us such that we're now comparing things to this, which is now set at our 0 mark. So that's our first rule. An element by itself is just going to have an oxidation number of 0. The second rule is pretty straightforward. It says for monoatomic ions, the oxidation number will be the same as the charge. So if I have a compound like NaCl, and I'm looking to figure out what these oxidation numbers are going to be, I'm going to assign oxidation numbers for sodium. I'm going to assign an oxidation number for chlorine. Well, a monoatomic ion, we should think about it as having those specific ions. So NaCl is really Na plus and Cl minus. Those are the charges that we're looking at. Rule 2 says the oxidation number for these monoatomic ions must be the same as the charge. So the charge on the sodium is +1, the oxidation number is -1. Chlorine, the charge is -1, the oxidation number is -1. Now, very, very important. Oxidation number and charge are not synonyms of each other. You cannot use them interchangeably. What this rule is saying is that the values happen to be the same, but they mean very, very different things. You can't use them interchangeably or as synonyms. So for monoatomic ions, look at the charges. The charges will equal the oxidation numbers. Let's do one more of that type. Fe2S3. Well, here we have an ionic compound again. So I'm going to work on assigning these oxidation numbers. Iron and sulfur. Well, an ionic compound, I should write out the ions that I have. Well, I have 2 iron ions, 3 sulfide ions. I don't know the charge on the iron right away, being it's a transition metal ion, but sulfur's in group 6A, so I know that those sulfurs are -2. That's going to make the iron, each one, +3. So now that we know the charges of the monoatomic ions, the charges will have the same value as the oxidation number. The oxidation number for the iron will be +3. The oxidation number for the sulfur will be -2. So it would work this way for all of the monoatomic ions that you're looking at. Our next set of examples are going to combine rules 3 and rules 4. Okay, rule 3 says the sum of each individual member's oxidation number is equal to the overall charge. Again, an oxidation number charge relationship, even though they're not synonyms, they're not interchangeable. So we're going to be using that rule. The sum of the oxidation numbers of all the different atoms and ions present will give you that overall charge. And we're going to combine this with rule 4 as well for a couple of examples where it says in compounds the oxidation number for oxygen is -2. So the first one we're going to do is CO2. And this one does a really good job of showing how oxidation numbers and charges are not synonyms. They're not interchangeable. This is a covalent compound. Covalent compounds don't have any ions. They don't have any charges. But we can still use oxidation numbers to describe electron richness and poorness. So we're going to use that combination of rules 3 and 4 to do CO2. So remember at the end what I'm looking for is I'm looking for the oxidation number of carbon and I'm looking for the oxidation number of oxygen. Well, rule 3 says the sum of all the parts kind of gives you the total. So what are these parts? Remember, these are not charges I'm writing. These are going to be oxidation numbers. Rule 4 says the oxidation number of oxygen is -2. And that's just what it is. In 99% of all the compounds oxygen's in, it's going to have an oxidation number of -2. We won't look at any exceptions to that. So that's what rule 4 was telling us. When you see oxygen in a compound, go ahead and assign it that -2. Now we need to use rule 3 now to figure out what's going on with the oxidation number of the carbon. We already got the oxygen's oxidation number is -2. What rule 3 says is that the sum of all of these oxidation numbers has to give you this overall charge. Well, the overall charge here is 0. It's a neutral molecule. Being it's a neutral molecule, the overall charge has to be 0. That means the sum of these oxidation numbers must be 0. Well, now I can kind of see, what do I have to have here for carbon to get this sum equal to 0? Well, I'm at -2, -4. The only way to get up to 0 if I'm at -2, -4 would be if the carbon is +4. So the oxidation number of the carbon is going to be +4. The oxidation number of the oxygen will be -2. Now here's what this rule is saying. The rule is not saying that these have to add up to the charge. It says that these have to add up to that overall charge. Because I have 2 oxygens, I have to take that into account. So in carbon dioxide, the oxidation number of the carbon is +4. The oxidation number of the oxygen's -2. Let's do another example that illustrates kind of this rule 3 and this rule 4 combined. And the compound I want to use for this one is KMnO4, potassium permanganate. So if I have KMnO4, I'm looking for at the end, remember, I got to figure out what is the oxidation number of the potassium, what's the oxidation number of the manganese, what's the oxidation number of the oxygen. That's what I'm looking for at the end of this. Well, this is an ionic compound. So ionic compounds, you want to think about what specific ions do you have. I have a potassium ion at +1, and I have a permanganate ion at -1. Well, right away I can kind of get some things in place in here right away that I automatically know. Potassium, monoatomic ion, kind of back to rule 2. Oxidation number is going to be the same as the charge, so the oxidation number will be +1. Now I have to work on the manganese and the oxygen. I know what the oxygen is going to be. It's going to be -2. That's what the oxidation number for oxygen is. But I need to use that information and kind of the sum of the parts equaling the total to figure out what's going on with the manganese. So I'm going to look at the parts of the manganese. I have 1 manganese and 4 oxygens. The oxidation number of each oxygen we already determined is -2. So that's going to be the oxidation number, not the charge of the oxygen, the oxidation number of the oxygen. I need to use that information to figure out what the oxidation number on the manganese is going to be. Here's where I use that sum of the parts equals the total. I need to take all of these parts, the oxygens and the manganese, and that has to equal this total. Sum of each individual member's oxidation number has to equal that overall charge. Well, I have to kind of sum together these parts and figure out what the manganese needs to be. This one's a little bit different. When we did the CO2 in the previous example, that overall charge was 0. Here, the overall charge is -1. So we need to get our sum total to -1. So what will the manganese have to be in order to get that sum total to -1? Well, -2, -4, -6, -8. I'm at -8. In order to get to -1, the only way I can go from -8 to -1 is if the manganese is +7. -2, -4, -6, -8 plus 7 gives me -1. That's my total. So the oxidation number of the manganese is +7. So for the elements in this compound, the oxidation number of the potassium is +1, the manganese is +7, and the oxygen is -2. So that's kind of how you use rules 3 and rules 4 in order to assign oxidation numbers. The next rule deals with the halogens. And it says most of the time halogens, remember halogens are those things in group 7A, fluorine, chlorine, bromine, iodine. The things in group 7A, those halogens, are going to have an oxidation number of -1, except when directly combined with oxygen. So let's start with how you usually see them. So usually you would see them not directly combined with oxygen. So in a compound like N2Cl4. Covalent compound, we want to assign the oxidation numbers for the nitrogen and the chlorine in this. Well, how are we going to assign those oxidation numbers? Well, the sum of the parts has to equal the total. Well, I have 2 nitrogens, 1, 2, 3, 4 chlorines. Using rule 5 that tells you that usually the halogens, and chlorine's a halogen, has an oxidation number of -1, I can right away get that oxidation number for chlorine in there right away. That means each of these chlorines will have an oxidation number of -1. Well, now I have to use that information to figure out what's going on with the nitrogen. Remember, the sum of all of these parts has to equal this total. Well, this is a neutral molecule, so the total up here is 0. So I need to figure out how I can get up to 0. Well, -1, -2, -3, -4. So I'm at -4 through all the chlorines. To get up to 0, that's going to mean each nitrogen has to have an oxidation number of +2. That's the only way I could get up to my overall charge of 0. That means the oxidation number of the nitrogen is +2. The oxidation number of the chlorine is going to be -1. So using how halogens usually appear at -1 and the sum of the parts giving you that total charge, that is how you usually see the chlorines. Bromines, iodines, fluorines, all the halogens. There is an exception to this rule though, and I want to do the exception because this exception actually comes up frequently enough that you kind of have to know about this one. So the exception says when it's directly combined with oxygen. So I want to look at a compound that has that be true for. So we're going to do calcium chloride, CaClO3-2. So remember at the end, what am I looking for? I'm looking for oxidation numbers for calcium, chlorine, and oxygen in this. So first off, this is an ionic compound. When you have an ionic compound, split it up into its ions. I would have 1 calcium ion and 2 chlorate ions. Well, calcium is a monoatomic ion, so that's kind of rule 2. Oxidation number for a monoatomic ion is the same as the charge. Plus 2 for the charge means the oxidation number will be plus 2. Now usually we would expect the chlorine to be -1 being it's a halogen, but we see it's directly combined with the oxygen, so that's not going to be true here. So what do you do here? Well, this is where there's kind of a hierarchy to the rules. Use the oxygen rule first. That's why we talked about it first. That's why it's higher on the list. Set the oxygen at -2. Then that's going to be used to tell you what the chlorine must be. So now both of these 2 chlorides, doesn't matter that I have 2 chlorides. I can just look at one because the other one's going to be identical to the first one I look at. Let's look at the parts. I have chlorine and 3 oxygens. I know what the oxidation number of each oxygen is going to be. It's going to be -2, so I can get that in there. Then I need that idea of sum of the parts is going to equal the total. The sum of each individual oxidation number has to give you that overall charge. So what has to happen? This sum of the 3 oxygens and the chlorine has to give me that charge. That charge is -1. So I got to figure out what does chlorine need to be to give me that charge of -1. Well, -2, -4, -6. So I'm at -6 from all the oxygens. In order to get to -1, this chlorine must be +5. It's the only way I can get up to -1. So now I have my last oxidation number. So in this compound calcium chlorate, the calcium has an oxidation number of +2, the chlorine has an oxidation number of +5, and the oxygen has a oxidation number of -2. So that's a key exception for the halogens that you need to be familiar with. The last rule that we need to see a couple of examples for deals with hydrogen. Hydrogen, usually we're going to see it as +1, where it is in most compounds, but there's a key exception to this, when it's directly combined with a metal. So first, let's look at how hydrogen is usually seen. If we look at something like SH6, sulfur hexahydride. Well, I want to figure out what the oxidation number of the sulfur is, and what the oxidation number of the hydrogen is. Well, how am I going to do that? Well, I'm going to use what hydrogen usually is. Hydrogen is usually +1 in compounds. Sulfur is definitely not a metal, so it's not going to be the exception. So I'm going to use this fact that hydrogen is +1 to figure out what's happening with the sulfur. For that, I need to look at all the parts. I have 1 sulfur and 2, 3, 4, 5, 6 hydrogens. We said that the hydrogens would each be +1 for their oxidation numbers. We need to then use that fact to figure out what's going on with the sulfur. Remember that it's this sum here, from the 6 hydrogens and the sulfur, that have to give you this overall charge. This is a neutral molecule. Being it's a neutral molecule, the overall charge is 0, so I'm trying to hit 0 as my goal. What does sulfur need to be for me to hit 0? Well, +1, +2, +3, +4, +5, +6. I'm already at +6. Being I'm already at +6, the only way to get to 0 would be as if sulfur was -6. So that's how I figured out the oxidation number of the sulfur is going to be -6 for this. So in this compound, sulfur will have an oxidation number of -6. Hydrogen will have an oxidation number of +1. So that's how you're usually going to see hydrogen. You're usually going to see hydrogen as just being +1. There are enough exceptions to this, and they come up often enough that we do need to be familiar with the exception. So I want to do an example of the exception to this rule. The exception says it's not going to be +1 if it's directly combined with a metal. So what is that going to look like? Something like LiH, lithium hydride. And this kind of comes from hydrogen's weird position on the periodic table. Remember, hydrogen is a non-metal, things like carbon, nitrogen, oxygen, but it kind of hangs out in that upper left-hand corner with some of the metals. So this example shows where hydrogen is not going to be a +1. And here's why it's not going to be a +1. If we look at this, lithium's a metal, hydrogen's definitely a non-metal. So whenever you have a metal and a non-metal, what type of compound do you have? Well, that type of compound is going to be an ionic compound. So we're looking at our oxidation number for lithium, oxidation number for hydrogen. So it's going to be an ionic compound. Well, lithium's in group 1A. You know, that likes to form +1. Hydrogen, though, remember, hydrogen's kind of the oddball. Even though it's in group 1A, it's still a non-metal. If lithium's already forming a +1 ion, hydrogen can also form a +1 ion. Hydrogen's also a non-metal. When non-metals combine with metals, they need to form negative ions. So the negative ion that hydrogen actually forms here is a -1 ion. Sometimes on periodic table, you'll see hydrogen in 2 places on the periodic table. Sometimes you'll see it in a standard position on the top of group 1A, but sometimes you'll also see it in group 7A right above fluorine, kind of as a reminder that, hey, this truly is a non-metal. So the reason why hydrogen's not +1 here like it is in a lot of the other compounds you see hydrogen in is because this compound's actually ionic. You're just going to use the ionic rule for this. Oxidation number will be the same as the charge. Oxidation number for lithium, same as the charge, +1. Oxidation number for the hydrogen, -1. So when hydrogen is directly combined with a metal, its oxidation number is not going to be +1. Instead, it's going to be -1. I want to do one last example that kind of re-illustrates a lot of these rules that we talked about and shows you how you sometimes have to be a little bit careful. The compound I want us to look at is this one, NaHCO3, sodium bicarbonate or sodium hydrogen carbonate. Now when you first look at this, you might be tempted to maybe go a little bit astray. You see sodium and you see hydrogen. You might say, that kind of looks like the exception for hydrogen. But what we're going to see is it's not going to be the exception for hydrogen. So we're going to use this one and we're going to assign all the oxidation numbers. So we have sodium we need to assign, hydrogen, carbon, and oxygen. So first off, this is not going to be an exception. Just because the hydrogen is next to the sodium doesn't mean it's directly bonded to, directly connected. You have to remember what these ionic compounds look like. This is an ionic compound where I have a sodium ion, and then this hydrogen is really part of this bicarbonate ion. These are not directly bonded to each other. The hydrogen is actually with the rest of its friends in this polyatomic ion here. Well, right away, can we assign some oxidation numbers? Sure. Sodium, monoatomic ion, oxidation number same as the charge, so +1. Now we have to go about figuring out the rest of these. Well, we know some of these already. Hydrogen, not directly combined with a metal, so it's going to do what it usually does and have an oxidation number of +1. We know what oxygen is going to do. Oxygen is always going to be -2. So we're going to use that information to figure out what the oxidation number is for the carbon. So we need to sum together all of these parts here. So I have one hydrogen, carbon, 3 oxygens. The sum of all these has to give me that overall charge. So we already know a lot of these. Hydrogen's oxidation number was +1. Oxygen's oxidation number was -2. So remember what we need to do for this. This sum of all of these has to equal this total. This time we have a charge as the total, and the charge is -1. So we need to get a total of -1 here. So we got to figure out, what does carbon have to be such that these will all sum up to be -1. Let's see where we're at. Oxygen's -2, -4, -6. +1, we're at -5 right now. So before the carbon we're at -5. That means to get to -1, the only option for the carbon is to be +4. These now will sum together for that -1. So the oxidation number of the carbon is +4. So now we have the oxidation number for each one of our compounds, or for each element in the compound. Sodium's +1, hydrogen's +1, carbon's +4, and the oxygen is -2 for this one. So you need to practice doing some of these, assigning the oxidation numbers on your own. Just kind of watching it isn't going to necessarily get the job done. You need to practice doing some similar type problems so you feel comfortable using these rules in assigning these oxidation numbers. So at this point that you can kind of resume the other video where we use some of this information to talk about some more oxidation reduction techniques and ideas.